Hi, my name is Michael Pendazis, and this is part 2 of the homework problems video for test number 2 in linear algebra, Math 231. So let's continue where we left off. We finished the homework problems in 4.2, and we're up to the problems in 4.3. And so in 4.3, the homework problems were number 4 and 11. And so let's look at number 4. Okay. So have your books open and look at number 4 in 4.3. It's on page 211. So the question is, in each part, determine whether the vectors are linearly independent or linearly dependent in piece of 2. And so A is the polynomial 2 minus x plus 4x squared. The other polynomial is 3 plus 6x plus 2x squared. And the other polynomial is 2 plus 10x minus 4x squared. And so the question is whether or not the set consisting of those three vectors is linearly independent in piece of 2. Okay? So if we take a constant, c1, times the first polynomial, plus the second constant, c2, times the second polynomial, plus the third constant, c3, times the third polynomial, and you set it equal to 0, well, what are the solutions for the c values that make this equation hold, to make this equation true? If it's only the trivial solution, all the c's are 0, and those three vectors in piece of 2 are linearly independent. But if there are non-zeros, if there are non-trivial solutions where not all the c's are 0, that means that those three do not form a linearly independent set, or that they're a linearly dependent set. So let's see. So if we add up all these things, you have 2c1 plus 3c2 plus 2c3. That's the constant term in the polynomial. The next term is negative c1 plus 6c2 plus 10c3. That's the coefficient next to x. And then the coefficient next to x squared would be 4c1 plus 2c2 minus 4c3 times x squared. And I'm going to put equal to 0 over here because I'm running out of room. So now I have a second degree polynomial. This is the constant coefficient. This is the coefficient of x, and this is the coefficient of x squared. And I want to see whether or not this equation can hold. So I get the corresponding linear system. 2c1 plus 3c2 plus 2c3 is equal to 0. Negative c1 plus 6c2 plus 10c3 is equal to 0. And 4c1 plus 2c2 minus 4c3 is equal to 0. So we get this corresponding linear system to that equation. Because in order for this polynomial to equal 0, each of its coefficients have to be 0, right? The 0 polynomial is 0 plus 0x plus 0x squared. And so this is 0, that's 0, and that is 0. So we end up with three linear equations from that one polynomial equation. And I'm going to have to switch markers here. So we want to find all solutions to this linear system. Okay, so its corresponding augmented matrix is 2, 3, 2, 0. Negative 1, 6, 10, 0, 4, 2, negative 4, 0. So that is the corresponding augmented matrix to that linear system. And we want to get this to reduced row echelon form. Let me do this. I'm going to multiply the first row by 1/2, and I'm going to get 1, 3/2, 1, 0. I'm going to take this row and add it to that one, and I'm going to get 0. I'm going to get 15/2. I'm going to get 11, and I'm going to get 0 here. And then I'm going to take negative 4 times this row and add to that one. I get 0, negative 4, and then it's going to be negative 8 and 0. Okay, now I'm going to take the second row and multiply it by 2/15. I'm going to continue over here, and I'm going to get 1, 3/2, 1, 0, 0, 1, 22/15, 0, And then I'm going to take 4 times this row and add to that one. And we'll get 0, 0, 88 over 15. 88 over 15 minus 120 over 15, which is minus 32 over 15. And let me just check that, that's going to be a 0, right? So you take 4 times this, multiply by 22/15, you get 88 over 15 minus 8, which is 88 minus 120, which is negative 32 over 15. Good, so that's what that is. And then you could simplify this to 0, 0, 1, multiplying this by negative 15 over 32, and you get a 1 there, and then you could add negative 22/15 to this row, and you'll get 0, 1, 0, and then this is a 3/2 here. You can multiply this row by negative 3/2 and add to that one, and get that to be a 0, and then you could add negative 15 over 32 to this row. 15 over 32 of this row to that, and make that a 0. In any case, you get the identity there. And so the only solution, therefore, is that C1 equals C2 equals C3 equals 0. And so that is the only solution to that equation is the trivial solution. And that means that these three form a linearly independent set. Okay, so these three, they form a linearly independent set. And that's because this equation only has the trivial solution, which is equivalent to saying that the vectors in that linear sum form a linearly independent set. Okay, and so part B is very similar to this problem, and so let's just keep moving. So that is number 4. I'm going to move on to 4.4 now. Okay, and so for 4.4, we have numbers 9 and 14. Okay, so numbers 9 and 14 for 4.4. Okay, so for number 9 in 4.4, it says show that the following matrices do not form a basis for M sub 2, 2. And so these are the matrices. Okay, that's one matrix. This is another matrix. 3 by 2 matrices. Okay, my pens are running low here. All 8 of them. I'm going to just try another one out. Okay, now 1, negative 1, 1, 0, and also 0, negative 1, 1, 1. Okay, so I have these 4 matrices, and the question is, do they form a linearly, show that they don't form a basis for M sub 2, 2. Okay, so in order to not form a basis for M sub 2, 2, they either would not span it, or they would not be linearly independent. So what I'm seeing is I have to do a lot of, we're going to have to work on do a lot with this problem. So So let me try to show that they're linearly independent and hope that that's what the problem is. A times 1, 0, 1, 1 plus B times 2, negative 2, 3, 2 plus C times 1, negative 1, 1, 0 plus D times 0, negative 1, 1, 1. So what I'm going to do is I'm going to take a guess as to why this doesn't form a basis. It's either going to not be linearly independent or not span M sub 2, 2. I'm going to guess that they're not linearly independent and hope that that's the reason that it doesn't work as a basis. So I'm going to make a linear combination of the 4 matrices that equal to 0 and find whether or not it has non-trivial solutions. Okay, And so if I combine these four matrices, I'm going to get this first entry is going to be A plus 2B plus C. This entry is going to be negative 2B minus C minus D. This entry is going to be A plus 3B plus C plus D. And this entry is going to be A plus 2B plus D. And so that's going to be the multiplying and adding up those four matrices and equal the zero matrix. That's what zero is, right? It's a zero. The zero in M2 2 is the 0, 2 by 2 matrix. Okay, so we get a corresponding linear system from that matrix equation that A plus 2B plus C is equal to 0. Negative 2B minus C minus D is equal to 0. A plus 3B plus C plus D is equal to 0. A plus 2B plus D is equal to 0. Okay, so so you get the corresponding linear system, and we want to know whether or not there are solutions. And so actually, there's I think let's do it the easier way. Let's take the coefficient matrix A. I'm gonna. The red marker doesn't write very. You can't see it, and it has plenty of ink. Okay, so the determinant of A is 1, 2, 1, 0. A is a coefficient matrix, and so I'm going to find its determinant. And when I do that, by the equivalent statements theorem, I will be able to determine whether or not AX equals 0 has only the trivial solution. Okay? So basically, if this determinant is non-zero by the equivalence theorem, it means that AX equals 0 is only the trivial solution, which means that they form a linearly independent set. So you can break this problem down to just find the determinant of this coefficient matrix. And so I'm going to take the cofactor expansion along the first row because there's a 0 there. And so, so this is going to be a lot of work. I'm going to take 1 times this is going to get the determinant of this guy. I didn't feel like solving a linear system, so I'm doing it this way. This minus 2 times, now you're calculating the determinant by this method. 1, 1, 1, 1. And so the problem is, so it's a bit more work. Okay. 1, 3, 1, 1, 2, 1. Okay, so now you just find that. Find the determinant of A. And so the determinant of this 3 by 3 matrix is, I'm just going to do some math here. Negative 1 minus 0. Negative 2 minus negative 1 times 3 minus 2, which is 1, plus negative 1 times negative 2. And so what that will be is negative 2, negative 1, 1. That determinant is 1. It's minus 2 times this determinant. This determinant is this determinant, and 0 minus, which is 1, times 1 minus 1, which is 0, plus negative 1 times negative 1, which is 1. That's also 1. And then plus this determinant, which is plus 2 times 0, plus negative 1 times 2 minus 3, which is 1. So you get 1 minus 2 plus 1, and that's equal to 0. So the determinant of this matrix is equal to 0. And so saying the determinant of A does not equal 0 is false. It's false to say the determinant is not equal to 0. And so that statement is equivalent to saying AX equals 0 has only the trivial solution. But that statement's also false. It has the same truth value. And so it's false to say that that this system only has the trivial solution, meaning all the A, B, C, and D's are 0. That's false. It has other non-trivial solutions. That means the original linear equation has non-trivial solutions, as these form a linearly dependent set. Okay? And so I like the way the determinant came out to exactly 0. It makes me more confident in that number, right? So determinant A is 0, which means it's false to say it's not 0, which means it's also false to say that this linear system is only the trivial solution. It has non-trivial solutions. That's equivalent to saying this equation is not trivial solutions. That's equivalent to saying your 4 original matrices are linearly dependent. And so they don't form a basis. So don't form a basis. Which is what you have to show. You have to show that they do not form a basis. Okay? Sorry. Okay. So they don't form a basis. Okay? So that's 4.4. Let's keep going. So 4.6 is 3 and 6, okay? Okay, so for number, so let's do number 3. So for number 3, in 4.6, page 235, it says consider these bases. B equals U1, U2, U3, and the basis B prime, which is U1 prime, U2 prime, U3 prime. So consider those 3 bases for R3. So these are bases for R3, where U1, where you have those 6 vectors there, right? U1, U2, U3, U1 prime, U2 prime, U3 prime in the book. And A is find the transition matrix from B to B prime, which the notation says looks like that. That's a notation for a transition matrix from B to B prime. Okay, and so the solution is the transition matrix from B to B prime. You can, one way to do it, there's more than one way, you can take, remember this is the old basis and this is the new one. And so you can take each old basis vector, and you could find its coordinates relative to the new basis. Okay, so you're just taking the coordinates of each old basis vector relative to the new basis. Yeah, good. Right? So you're taking each old basis vector and you're finding its coordinates relative to the new basis. Okay, and those are the corresponding columns 1, 2, and 3 of the transition matrix. So how do you do that? So it's the coordinates of U1 relative to the new basis B prime are the components C1, C2, C3 that satisfy this equation. Okay, so the coordinates of U1 relative to the new basis B prime is C1, comma C2, comma C3, where they satisfy this equation. And so C1 to U1 is this vector 2, 1, 1. U2 prime, no, U1 prime is 3, 1, negative 5. 3, 1, negative 5. The next one is 1, 1, negative 3. Negative 1, 0, 2. Okay, and so U is this. Okay, so then U so U1 is 2, 1, 1. So you just have to solve this for C1, C2, and C3. And so you get the corresponding linear system 3C1 plus C2 minus C3 is equal to 2. C1 plus C2 is equal to 1. Minus 5C1 minus 3C2 plus 2C3 is equal to 2, is equal to 1. Okay, so you get that linear system, and you find all its solutions in order to find the coordinates of U1 relative to the new basis B prime. Okay, and so okay, so finding the solutions, you have C1 plus C2 is equal to 1. And if I add 2 times this equation to this equation, I'm going to get C1 minus C2. This is going to cancel with this, and I'm going to get C1 minus C2 is equal to 5. Okay, and so that will mean that if I take the negative of this and add to that, I'm going to get negative 2C2 is equal to 4. Okay, so I'm just solving this linear system for all the solutions like we've done plenty of times. C2 is equal to negative 2, and if C2 is equal to negative 2, then C1 is equal to 3. And if C1 and C2 are those values, then I just plug them in here, and you get 9, 7, C3 is 5. Okay, and so those are the values of C1, C2, and C3. So the coordinates of U1 prime, U1 relative to B prime is equal to 3, negative 2, 5. And so this is the matrix whose first column is 3, negative 2, 5. And now we just need to find the other 2 columns. And so we're going to do the exact same process, but now we're going to do it for each of the other 2 coordinate vectors. Okay, so now we want to find U2, the coordinates of U2 relative to B prime. And so U2 is equal to C1, using new C1, C2, C3s. U2 is equal to C1 times U1 prime plus C2 times U2 prime plus C3 times U3 prime. And so that's going to equal C1 times U1 prime, which is again 3, 1, negative 5, plus C2 times U2 prime, which is 1, 1, negative 3, plus C3, which is C3 times U3 prime, which is negative 1, 0, 2. Okay, so now we're just going to, and U2 again is, U2 now is 2, negative 1, 1. Okay, and so you get the corresponding linear system 3C1 plus C2 minus C3 is equal to 2. C1 plus C2 is equal to negative 1. Negative 5C1 minus 3C2 plus 2C3 is equal to 1. So you get that linear system. Okay, so now, the second one, I like the second equation because C1 plus C2 equals negative 1. Let me leave that alone. Let me get rid of the C3 by taking 2 times this equation and adding it to that one. And so I'm going to get, that the C3 is going to cancel. I'm going to get equals 5 again. And then I'm going to get negative C2, C1 minus C2 is equal to 5 now. And so if I take, I'm going to do this way, I'm going to add this to this, I'm going to get 2C1 is equal to 4, C1 is equal to 2. That means that C2 is equal to negative 3, because then 2 plus negative 3 is negative 1, 2 minus negative 3 is 5. That's C1, C2, and then if I plug them in, I'll get 6, 3, I'll get C3 is 1. Okay, and so I'm just solving this linear system of solutions like you would normally do. So that means that C1 is 2, C2 is negative 3, and C3 is 1. Okay, and now the third column is just you take U3 and you set it equal to a linear combination of U1 prime, U2 prime, and U3 prime. And so now U3 is going to be the matrix 1, 2, 1. And it's going to be a linear combination of that. And so I'm going to get that this is equal to 1, this is equal to 2, and this is equal to 1. And so now C1 plus C2 is 2. And then I'm going to just erase this now. So I'll just redo this part. And then, I'm going to take 2 times this and add to that. And I'm going to get equals 3. And then I'm going to get minus C2. C1 minus C2 is 3. I'm going to add them. I'm going to get 2C1 is equal to 5. C1 is equal to 5 halves. And that means C2 is equal to negative 1 half. Okay, so you're just finding the solutions to that linear system. 5 halves minus 1 half is 4 halves, which is 2. And then plugging them in here, I get 15 halves. 7 1/2 minus a half is 7. Right? So 7 1/2 minus a half is 7. 7 minus C3 is 1. So C3 is 6. 7 minus 6 is 1. So now C1 is 5 halves, and that goes here. C2 is negative 1 half, and C3 is 6. Okay, so that's the transition matrix from the old basis B to new basis B prime, and that's part A of this example, okay? And then, okay, so now the transition matrix. So for part B, we're going to take the transition matrix and compute the coordinate vector of W relative to B. Okay, so W is equal to negative 5, 8, 5. That's W. And then we're going to compute the coordinate vector of W relative to B prime. Well, that's just equal to the transition matrix from B to B to B prime times the coordinate vector of W relative to B. Okay, it says use 12 in the book. 12 is just that equation. Okay? And so you have to find the coordinate vector of W relative to B. So to find the coordinate vector of W relative to B, it's just equal to C1, C2, C3, where this is going to equal C1 times, and so you're going to find it relative to relative to basis B. So U1, so this is going to be 2, 1, 1 plus C2 times 2, negative 1, 1 plus C3 times 1, 2, 1. Okay? And so we're just going to find C1, C2, and C3 that make W equals C1, U1 plus C2, U2 plus C3, U3 true, hold. And so it's just solving a linear system. See, the corresponding linear system is 2C1 plus 2C2 plus C3 is equal to negative 5. C1 minus C2 plus 2C3 is equal to 8. And C1 plus C2 plus C3 is equal to 5. That's a corresponding linear system that will satisfy the solutions for the C's will satisfy that equation. And so finding the solutions to that system, let me take negative, I'm just going to quickly find the solutions to it. So I'm going to get 18 is equal to negative 5C2, negative minus 3C1 minus 5C2 is equal to 18. I'm going to add negative to this. I'm going to get 10 is equal to negative C2 there, and a minus C1 here. Okay, so now I have two equations with two unknowns. I'm going to take negative 3 times this and add to that, and I'm going to get negative 2C2 is equal to negative 12. So T2 is equal to 6. And if C2 is equal to 6, that means C1 is equal to negative 16. Okay, so then that's 16 minus 6 is 10, good. And then 48 minus 30 is 18, good. So that's C1, C2, and then C3, and just plug this in here, negative 16, negative 10, C3 is 15. Okay, so that's C1, you're just solving a linear system, however way you want to solve it. So the coordinates of W with respect to the basis B, which is C1, C2, C3, is negative 16, comma 6, comma 15. Okay, that's the coordinates of W relative to the basis B. Okay, so C's that satisfy that equation. And so now, in order to find what the coordinates of W is relative to B prime, just take this coordinate matrix, 3, 2, 5 halves, negative 2, negative 3, negative 1 half, 5, 1, 6, and multiply it by this, which is negative 16, 6, 15. And when you multiply those two, you'll get the answer, and that answer is, you can get a 3 by 1 matrix, and so you multiply this out, you get negative 48 plus 12 is negative 36, negative 36, negative 36 plus 37 and a half, negative 36 plus 37 and a half is 1 and a half. So that's 3 halves here. And then 32 minus 18, 32 minus 18 is 14. 14 minus 7 and a half is 6 and a half, which is 13 halves. And then negative 80 plus 6 is negative 74. Negative 74 plus 90 is 16. Okay, so let me just check. Negative 48 plus 12, negative 36. Negative 36 plus 75 halves, which is 37 and a half. Negative 36 plus 7 halves, 3 halves. 32 minus 18 is 14. 14 minus 7 and a half is 6 and a half, or 13 halves. And negative 90, negative 84. Negative 84 plus 90 is, wait, no, negative 80. Negative 80, negative 74, and negative 74 plus 90 is 16. So that's it. Okay, so the coordinates of W relative to B prime is that. Coordinate vector of W relative to B prime is that. And in part A, that is the transition matrix from the old basis B to new basis B prime. So that's A and B of that. And for C, you just check your work. So if you find the coordinates of W relative to B prime directly by taking a linear sum of U1 prime, U2 prime, U3 prime, and finding the C's, you can get it that way also. So that's C part C is checking. And so I'll stop with that. Okay? And so that is 4.6. Okay? And so I'm going to post one more video, and that will conclude the homework problems for chapter 4.